So just as we did with looking at the negative electrode, we now look at aging mechanisms in the positive electrode to get an idea of what might happen there, why a positive electrode might degrade. And again, we can think of this as in three different ways. So aging at the particle surface, aging within the active materials themselves, and aging then in the overall positive electrode composite structure. Looking at the surface of the particle first, we said in the negative electrode there would be a side reaction between the solvent and the material forming the active particles, and that formed an SEI layer. And there is some evidence that this happens in positive electrode materials as well, that there is some kind of an oxidation that happens, in this case with probably the LiPF6, the salt in the electrolyte, that forms a surface layer, and that surface layer then being resistive and losing lithium capacity in the process. This is not nearly as pronounced as it is for the negative electrode. So there is universal agreement that SEI forms on the negative electrode particles, and I'm not sure that there's universal agreement that something like that happens on the positive electrode, although there is evidence to say that it does. It's just not as well understood and not as pronounced. A bigger factor in the positive electrode, especially with certain types of positive electrode chemical structures, is that they can fall apart. Maybe not fall apart, they can be attacked by the electrolyte, and it doesn't cause the formation of a film in this case. It actually just causes a deterioration of the electrode, the manganese or the cobalt or whatever that forms the positive electrode itself dissolves into the electrolyte, and then we have positive ions floating around, Mn2 plus or whatever, floating around in the electrolyte, and products involving these metals can be formed on the surface either of the positive or the negative electrode as a high resistance film. So we kind of previewed that in the last section, and here just reviewing that idea. And with LMO electrodes, lithium manganese oxide, this is probably the main deterioration mechanism of the positive electrode, because manganese is relatively unstable in the electrolyte, especially at high states of charge and at low states of charge. When we dissolve manganese, and it happens with cobalt too, although to a lesser extent, when we dissolve these metals into the electrolyte, we have capacity loss, because I used to have all these storage locations for lithium, but all of a sudden this one dissolved. It's not there anymore, so now there's fewer places to store lithium. And the metal can poison the negative electrode, meaning that it goes and attacks the Mn2 plus, would go over to the negative electrode and attack it, and cause SEI to grow, to block pores, to do a number of possible things. So the mechanism of the deterioration and the poisoning depends on which oxide is used in the positive electrode, but it tends to happen mostly at low and high states of charge, and it can be greatly accelerated by high temperature. The actual mechanism is probably an acid attack, and we mentioned this in the last section, that trace water, so H2O plus LiPF6, produces stuff including hydrofluoric acid. And this hydrofluoric acid is nasty, and it will attack the surface of the manganese. So I've got LiMN2O4 for LMO, and inside of this manganese structure We have, if you remember pictures from last semester, we've got these interesting shapes of how the electrons and the atoms are bonded together inside of the crystal structure. And inside of this, the manganese is nominally at a 3+ oxidation state inside of this. However, just due to electron motion and so forth, some of them could be in a 4+ state and others could be in a 2+ state. And these 2+ ones form with the hydrofluoric acid, and it dissolves the manganese into just Mn2+ in the electrolyte. So that's probably not nearly well enough explained to give an idea, but it's just electrons moving around, and it tends to happen more in certain states of charge when the lattice structure, the crystal structure of the electrode is stretched or strained in some way that causes the greater likelihood of having a Mn2+, and that Mn2+ then just easily dissolves into the electrolyte. And then it's gone, and then the structure is gone, and I can't store lithium in that particular location any longer. So that's the surface effects. Now we look at within a particle itself, and I just alluding to this just a few seconds ago. When we charge and discharge the material, putting lithium in and taking lithium out, it causes distortions in the shape of the structure, and they're not necessarily uniform in every direction. They could be anisotropic, so they could have different strain and stresses in different directions. This is called a phase distortion. If I go into what might be called a cubic phase to a tetragonal phase, anyway, it's a different shape of the structure, and that causes strains that can lead to cracking. And the transition between one type of phase and another type of phase is caused by the presence or absence of lithium in the storage sites. So I've got different local molecular forces. So some of these phase transitions are completely normal and generally reversible. It's mostly if there's perhaps some kind of a defect in the structure, as is unavoidable when you're manufacturing this stuff. You can't make it perfectly, that the stresses and strains would accumulate over time and cause some fracture and breakage, some cracking. There are other types of strains that can actually lead to collapse. We've mentioned that LCO, which is lithium cobalt oxide, I think it's COO2 is usually what's used as the formula, if I remember, forms in layers. So I've got layers of this lithium cobalt oxide, and lithium intercalates in between these layers a lot like it intercalates between layers of graphene in the negative electrode in the graphite structure. The difference is that I can pull all of the lithium out of the graphite, and I can then put it back in, and that works fine. But if I pull all of the lithium out of LCO, these layers will collapse, and maybe not totally, but they will collapse to the point where there's not room any longer to put lithium back in. I need to have a few lithium in here to act kind of like pillars that support the structure, that make sure that it doesn't collapse. So if I take out too much lithium, then I get layers collapsing, and I get a capacity decrease because I can't put lithium back in to those layers. So that happens. So remember, if I pull too much lithium out of the positive electrode, that means my cell overall is overcharged. So when I overcharge a cell, this is one thing that can happen. Something else that can happen is known as structural disordering, and that's, we have crystal structures which we visualize ideally, but of course there are, as I mentioned, there's defects, and we have non-ideal structures. And it's possible with the stresses and strains and collapses and so forth, for some of the bonds that make up the crystal structures to break down, and they could reform in different ways. So where I had a nice, beautiful crystal structure with things all beautifully connected, well, something could break and I could connect this to somewhere else instead, and I lose the ability to store lithium because I've lost a lithium storage site. So if you go back to the previous course, especially the Battery Bootcamp Chapter 1, where we've got pictures of the crystal structures, we remember there's tunnel-like mechanisms in some crystals that lithium goes through the tunnels, others have layers, and so forth. But if I collapse these tunnels or layers, I can't get lithium into or out of that part of the crystal anymore, and I've lost capacity. So lithium might be trapped, so I can't use it, or I just don't have anywhere to store it anymore, so I've lost capacity either way. The phase distortions that we've talked about of the stretching and shrinking of the material causing different types of crystal structures, when they happen near the surface, I guess there's more room to expand and contract there. You could think of it that way. We could lead to a permanent change in the structure. And we could have some layers where the outer layer of the particle is different in structure from the inner bulk layer of the particle. And it could even happen kind of subsurface, so underneath the main surface I could have a layer of change, and there's some evidence that says that can happen in some materials. Again, these different distorted structures would impede the ability for lithium to flow. It may still be able to move, but maybe not quite as freely as before, leading to a higher resistance. And an interesting property of crystals is they tend to grow over time. That, crystal of a certain material in contact with a crystal of the same material over time tends to form a single crystal. And some materials, for example, I think this picture is of lithium iron phosphate. The unaged, if you can see this picture, has lots of little tiny particles in it, but the aged one appears to have fewer particles and bigger particles. They've kind of grown together. And this doesn't change the capacity necessarily, but it does change the surface area. Because bigger particles have lower overall surface area for the electrode, and that means that the resistance of the cell is going to go up. So we've seen surface effects, bulk effects. Now we look at the and now we look at the composite electrode. And we also notice degradation in the inactive components of the cell. So the binder, the kind of rubber that glues the particles together, can decompose over time. So I lose some contact between particles maybe, which at minimum increases resistance, but also may lose capacity if I completely lose a particle from the lattice. I can't get to it any longer. There can be oxidation or chemical reactions of the conductive particles. So this is the chemical binder like PVDF, and this is like the carbon black, which is C6 ground up really fine and thrown in as a surface coating of the positive electrode to make it more electronically conductive. The positive electrode materials tend to have very poor electronic conductivity, so we add some additives to allow the electrons to move. But if this carbon black that's added chemically decomposes, the electrons can't move as freely any longer, and I have higher resistance. The current collector can corrode as well, react with its environment. I think it's less prevalent in the positive electrode than the negative, but it can happen. And again, we can lose contact to our particles because of stresses and strains of volume changes. There's some kind of delamination from the current collector or from particle to particle. Again, I present a table. This is adapted from the paper by Vetter that talks about aging in the positive electrode. And I think we've talked about most or all of these, and I will leave you to read this summary table. So overall, I hope this has at least been somewhat helpful in dispelling the mystery of why cells age. Lots of different reasons. There's not just one reason why cells age, and so more than one of them is happening at a time. This makes it pretty challenging if we want to do some advanced battery controls. If there was only one way that cells aged, then we could maybe make a mathematical model of how that worked, and then we could use that mathematical model inside of some optimization procedure to optimize how we charge a battery cell or discharge a battery cell or so forth. And then we could probably impact the life of the cell. At least in principle, we could impact the life of the cell and get great performance out of it for a longer period of time. And part of our research and our research team right now is really focused on that, is modeling the degradation mechanisms and using that knowledge to attempt to come up with control means to make a battery cell last longer. The challenge, or one of the main challenges, is that there are so many possible degradation mechanisms that it really isn't feasible to model all of them. And you need to model only a few, the ones that you think are most important, the most severe. And so we think we're making some progress on that and developing controls. So that's another reason why knowing about aging is a good idea, but I think it's just generally good background information going into the battery management profession to understand, well, I at least have an idea why batteries age and why it's important to estimate the aging of the battery so that we can keep up to date on our energy estimates and our state of charge estimates and our power estimates and so forth. So what we're going to do next is we're going to start thinking about how easy is it, how observable is it, are these degradation parameters to see how easy it might be to estimate their values, and we'll spend the rest of the chapter looking at different ways of estimating capacity fade and power fade.